Okay, welcome back. So now Kyle has shown you how to create the other enantiomer, right, with this process on the board. And I would like to do some more practice for this type of anti-addition of you guys. So essentially halogenation is a so-called stereospecific process. Right? Remember, we have seen other stereospecific processes. For instance, SN2 reactions, right, where you start, for example, where you always get inversion of configuration. Right? That the other thing we have seen as a stereospecific process was, for example, E2 elimination. Right? That can be either stereospecific or stereoselective. And we've seen that. Now, why is it stereospecific, this kind of anti-addition to the double bond of halogenation? Because the stereochemistry of the product, the products, is determined precisely by the stereochemistry of the starting materials, right? And that's always true for a stereospecific reaction. You go from one stereochemistry in the starting material to one specific stereochemistry in the product. Okay, so let's look at an example. If we start, for example, with this alkene, again, make sure you can name these things. So this would be a butene. It's a cis-2-butene. It's the name of this compound, right? If we react cis-2-butene with Br2, with dibromine, what we get, think about what we get. We have the bromine, some will come from the front to make the bromonium ion, and then the Br minus opening that bromonium up from the back side. So one of the bromines is now pointing to the front and one bromine is pointing to the back. You see how these two bromines are on opposite sides? One coming forward, one coming backwards, so they are anti to each other, right? And then of course we form the other enantiomer, where the first bromine on the left is pointing back and the other bromine on the right is pointing to the front, right? You always form these enantiomers. Make sure you can actually draw the mechanisms to form both enantiomers. It's important. You see, the key here is that the bromines are on opposite sides of the double bond added, and so that's why they're anti. Right, so we form two enantiomers in this case. Now look at what happens in contrary when we start with trans-2-butene. Something different happens. And again, we reacted with bromine, with Br2. Sorry, this should be Br2. This is wrong, okay? Please make sure you write Br2 there. And let's see, I think I can probably write it too here. Let's see. Yes, okay, that worked. So that's Br2. Now here you see we again add the we draw the trans arrangement of those methyl groups, and they're anti-periplanar to each other, because initially the two methyl groups, because you start off with having the two methyl group trans. We just kind of redraw that trans arrangement, and now the bromines again add anti, right? So one bromine coming forward, the other bromine going back. And now you might think, all right, what about the other enantiomer? The thing here is, the tricky part here is because of the compound now has symmetry. It actually is a meso compound, and it doesn't have an enantiomer. So I'll show you why. All right, so you see this compound, you can rotate around this central carbon-carbon bond, so that in the end, the two methyl groups and the two bromines are on the same side. So that they are actually eclipsed with each other. Both bromines are eclipsed, and both methyl groups are eclipsed, and both hydrogens there are eclipsed. So now you see this, if drawn in this conformation, you actually have a mirror plane, which goes right through the middle of the molecule, and that's, of course, what you immediately recognize as meso. Right? And so meso compounds, as you know, they are achiral, and so that's what happens. So this is a tricky business, right? Depending on what kind of symmetry you get in your compound, and whether you start from the cis or the trans olefin, cis or the trans alkene, you get different stereoisomers of the product. You have to be very careful. Sometimes you have an enantiomer you form, sometimes you don't, depending on whether the compound is meso or not. So I really recommend you practice this more at home than with conceptual checkpoint 8.20, 820. Okay, so next we are going to look at the variation of this bromine addition reaction. What we're going to do is we're going to look at what happens if you do a reaction of an alkene with bromine or with chlorine in the presence of a lot of water. Okay, and water is going to be the solvent. So then what we're going to form is so-called bromohydrins. What's a bromohydrin? Bromo is we have a bromine added, and hydrin is we have a water added. Okay, so we add OH and the Br at the same time. Mechanism is very similar to what we just discussed. It's just a minor variation. There's a couple tricky parts to this the bromohydrin formation, including regioselectivity. Right? We didn't have to worry about regioselectivity in the bromine addition because you just add two bromines to both carbons of the double bond, and so regioselectivity really doesn't matter. The only thing which matters is you do it in an anti-addition for the Br2. But now if you add a Br and an OH, then it matters which side you add the Br2 and which side you add the OH2. Okay, and so this bromohydrin formation happens if you do bromination in a lot of water, and water is the solvent. Why does it happen? Again, then because you have so much water present, because water is the solvent, and yes, it's there in much larger amount than the Br minus or than the bromine, and so then actually the water is what's going to trap, what's going to be the nucleophile to attack the bromonium ion. Right? So just the second part of the mechanism is going to be different. Okay, so let me show you what happens. So first, then we're going to look at the regioselectivity of this process. And essentially what we are going to see is that what's going to happen is that the water is going to attack the side with the more substituted carbon atom. Kind of like if you had a Markovnikov addition. Okay. Pretty much just a Markovnikov addition of Br plus and OH minus. Okay, and why again does it go the nucleophile then to the more substituted carbon, the water, which is the nucleophile? Because like in every Markovnikov addition, the carbocation is more stable. The partial carbocation is more stable on the more substituted carbon. That's just carbocation stability. Let's look at an example. I'm going to start with this olefin, and first we're going to react with bromine, Br2, right? And so we're going to have bromonium ion formation like before. So we form the bromonium ion, and Br minus is the leaving group, nothing new, and here is just pretty much just drawing out the bromonium ion. Now the key thing is there's actually an important resonance structure for this bromonium ion, where we basically break one of the carbon bromine bonds, and we can draw a tertiary carbocation in this case on that carbon atom, right, and move and make the bromine neutral. You see that? So those are resonance structures. So it's important to realize that we're going to break the carbon bromine bond in these resonance structures with the more substituted carbon only, right? Why? Again, that's just because putting the positive charge on the primary carbon atom would be much less favorable, right? It's not a good resonance structure. So this resonance structure here, you don't want to draw. See where the positive charge is on that primary carbocation. Where you can make a primary carbocation, you know that. Okay, so this means there is a fairly strong partial positive charge because of this resonance structure on the right up there. There's a fairly strong partial positive charge on the tertiary carbon atom, which is attached to the carbon, which is attached to the bromine. Okay, and so this means the water will now attack that carbon in the second step. Okay, so the water attacks the more electrophilic tertiary carbon. And here's how it looks. I'm just redrawing the bromonium ion here. Putting the water up there. Giving you a couple seconds to draw it. Okay, and so now the water is the nucleophile. It attacks the tertiary carbon atom, and it opens up the bromonium again from the backside, like before. It's pretty much just an SN2 reaction with Br plus, or Br as the leaving group. Okay, and Br is a better leaving group than Br minus, of course. So the product we form looks like this. You open up the carbon-bromine bond. Now you have water attached, but of course the oxygen of the water carries a positive charge. Like whenever this happens, whenever water acts as a nucleophile and attacks the carbocation. So now in the last step, what do you think needs to happen? We just have to deprotonate that oxonium, so-called oxoniumide, that protonated water. And what is the base which does it? It's another water molecule. Well, it could be the Br minus form in the first step. So either Br minus or another water is acting as the base. So we're going to draw it here with water. Again, oxygen, the water is the base. You do the standard deprotonation, and now we form the product. So you see we're getting an OH group on one side and the bromine attached to the other side of the double bonds. Again, the key is to put the OH group on the side on the more substituted carbon in this mechanism, and again have anti-addition. So I would like you now to think about another example. What are the products of the following reaction? Here's the reaction. I'm going to take an olefin, Br2, and water. What forms? Take about 5 minutes to think about this. This is not a super easy problem. Think about all the products which can form. Again, think about stereoisomers and stereoselectivity, stereospecificity, regioselectivity. Okay? We'll reconvene in a couple of minutes.